In this clip, we're going to look at how to construct, or how to calculate rather, the volume of the region bounded above by this surface right here, 10 plus x squared plus 3y squared, over this region right here. So this is going to be the rectangle where x is between 0 and 1, and y is between 0 and 2. And we'll compute this using a double integral. So first off, the volume is going to be the double integral over this region of this function given by z here with respect to area. So this dA here is just kind of a placeholder symbol that says that that's going to be what we call an area element. And we'll see what that means as we write it down. So I can write this as, let's see, the integral from 0 to 1, so that's going to be for the x domain, and then the integral from 0 to 2, so that'll be for the y domain, and then I'm taking this upper surface to be a function in x and y, so this guy, and so then y is the one going between 0 and 2, and x is the one going between 0 and 1. So just notice that this guy here is matching that y goes between 0 and 2, and this guy here is matching up with the fact that x is going between 0 and 1. Okay, so that's the way to write it, and then how to compute it. Well, what we're going to do is essentially partial integration. I mean, nobody calls it that, but I'm just trying to make an analogy with partial differentiation. So what I mean is we're going to look, just keep the dx part by itself and look just at the y part. And inside this, so for this inner calculation right here, we're going to look at this one as, actually, here, let me put it on the bottom, this part right here. This is going to be, think about this as we keep x fixed for the moment. So this is like, we're doing a little calculation for some fixed value of x between 0 and 1. So in other words, what I mean is treat x like a constant. Just exactly the same way that you would when doing a partial derivative with respect to y. So now we're just doing the integral with respect to y. Okay, so we work out that inner integral, and it turns out that we get, let's see, so that first part there, 10 plus x squared, that's just a constant with respect to y. So we integrate it to get a y right there. And then we integrate the 3y squared part, and that integrates up to being y cubed. And then we have to evaluate that from y going from 0 to 2, and we leave the dx stuff outside, just sort of dangling along. Okay, and continuing on our merry way, so bring the integral from 0 to 1 along, evaluating this guy inside the parentheses, where y is equal to 2, we end up with, let's see, collecting terms, 28 plus 2x squared. And then when we evaluate it at y equals 0, that whole thing zeroes out because each term has a y. So we just have this guy. And then at this point here, notice that this has no more y's. We've integrated out the y's, all right? And now we can just go ahead like we're in single variable calculus and integrate this sucker. So we integrate the 28 and we get 28x, and we integrate the 2x squared and we get 2/3 x cubed, and that's evaluated from 0 to 1, and we end up with, turns out to be 86 over 3 when the dust settles. Okay, and so the picture that goes along with this is that we're on this rectangle here from this rectangle 0 to 1 and 0 to 2. And then we've got a function, and it actually looks something a little bit like this. Let's see, so we've got there we go. If I've drawn it right, something like that. And the first thing that we did is we looked at what was going on for a particular y value. So if we just like mark off this y value right here as our generic y value, we worked out the integral for let me draw a slightly different y slice so that it just draws better. There we go. And so we've got this little, that's that cross section right here. And then now let's draw a picture of what this looked like. This looks something like this. So we've got out from 0 to 1, and then across 0 to 2. And the surface of this function is up here somewhere. So it looks something like that. And then what we did is it was like we fixed some x value momentarily, and we looked at this slice, and so that inner integral is cooking up the area of this cross-sectional slice right here, and so the area is, let's call it a of x. And that's exactly this right here. This formula here is our a of x. That's the area of the cross section at a fixed value of x between 0 and 1. And so when we integrate that from 0 to 1, it kind of sweeps out that region. And I'll show you an animation in just a moment. But first, I want to go back and show you that the magic is that it doesn't matter which order you do it in. So this notation right here is deliberately vague because you can set it up to do the integral with respect to y first on the inside or x first. So let's just check that, and we'll do it the other way around. So v is also equal to integral from 0 to 2, 0 to 1, 10 plus x squared plus 3y squared dx dy. And now you can see again that I'm matching the dx here with the fact that x is between 0 and 1, and I've moved the dy to the outside. So this is y between 0 and 2. Okay, and so now I first do like this quote-unquote partial integration with respect to x. And so that gets me the integral from 0 to 2 of, and then that thing on the inside, integrating with respect to x now, 10 and 3y squared are both constant terms. So I've got 10 plus 3y squared x. Constant becomes a linear function. And then I've got x cubed over 3. And this is going to be dx. And so then if I integrate that with respect to y, oh, sorry, I skipped a step here. I have to evaluate this from 0 to 1. Sorry about that. And so when I do that, I get the integral from 0 to 2 of 31 over 3 plus 3y squared dy. And then I can do that integral just like I was in a a single variable calculus course back in Calc 2 or something. And that should be a 3. So I get 31 over 3y plus y cubed, now evaluated from 0 to 2, And when I work it out, sure enough, I get the same 86 over 3. And let's just box it in red for good measure to make it look fancy. And so what I've done over this time is let me recreate my little plot there. So here's that same surface. Something like that. So this time what we did is we crunched out what the we fixed some y value on the y-axis here, and we took a slice and we figured out what the cross-sectional area is at that particular value of y. And so we just and that's exactly what we found here. So that's the area of this object as a function of y at a particular y coordinate. And so what we're going to see in the next clip is that this always works out. This is always equal back and forth. As long as the function that you're integrating is continuous, you'll never have to worry. So I wanted to show you a little animation here. That what you're looking at is Mathematica, and I've had it plot for me the function x squared sine of y, and it's just so you can look at what it looks like if we integrate it in one order or the other. So if we are integrating dx first, then what we end up with is the formula for this green slice as a function of y for a fixed y coordinate as y runs down the axes here. I think I've got this going from 0 to 2 pi. And so here I'll just let it run. You can kind of see what it does. Unfortunately, it loses a little resolution when it's in animation mode, but it's that that green slice running down the y-axis. Okay. Now, on the other hand, if we integrate dy first, then when we integrate dy, it sweeps out this green slice that you see right here. And then when we do the second integral, that slice is going to come out the x-axis, and it will sweep out the same volume as it goes all the way through. And so each one of those green slices that you're seeing there is the area at a fixed x coordinate. Okay, so hopefully you can keep that in mind when you're thinking about how this thing is set up, and you kind of want to imagine that surface, or sorry, that green sheet, like sweeping through every point of the solid whose volume you're trying to find.